Okay, so in yesterday's lecture, I show how to, for a kind of a generic, from a generic nonlinear wave system, how do we get to the wave kinetic equation? Okay, so that is okay. Okay, well, this guy has a constant, I think it's 4 pi, no, 2 pi. And so our vectors. Okay, so where I remind you what is this? This is the nonlinear part, so nonlinear matrix. So you take your original PDE, kind of the microscopic dynamics. You write it everything in a kind of canonical way, and this is what encompasses all the interaction of the waves. And this was for a particular type of interaction. This is the one we usually find in hydrodynamics, where you have three wave vectors, K1, K2, and K3, okay? So this is what we call three waves interaction. So what I want to show today on the blackboard is what we can say from this equation, how we can predict things in a very general framework. And then the second part of the lecture, I will go more to the example of inertial and internal waves, okay? And to try to tell you what we know from this system, okay? So this guy here, it's omega k minus omega 1, omega 2, okay? So the idea that you have a wave that carries an energy omega 1, omega 2, and omega 3. So it's conserved energy, something that I'm going to show in a second, okay? What else? Just to make it a bit easier later, this parenthesis here, you can write it as nk, n1, n2. Just factorize these three, and you will just get 1 over nk, 1 minus n2. Okay, this is, I will use it a bit later. So the first thing you would like to see is, so initially we have an equation that conserves, obviously we say that conserve energy, okay? So it's the natural things to say, what if there are conserved quantities by this equation, okay? It's going down all the time. Okay, we'll go here. Okay, what are the basic properties of the kinetic equation? Before finding some solutions, we just, perhaps the most important in this case is the energy. So remember that the energy, the leading order is just the quadratic part of the energy, the total energy, which you can just write as omega k dk. This is a conserved quantity. Okay, how do you show that? As typically, you just do dE by dt. You use the kinetic equation, and you will get omega k LK12 have an extra integral from here, dk, dk1, dk2. But k, k1, k2, they are just dummy indices. So I can rename here, for instance, I can call, I can exchange k, rename k with k1, here k with k2, and then I can refactorize everything. So I say k1, 2, 3. Okay, we keep the same k1, k2, dk, dk. But if you remember, inside this guy, there is a Dirac, okay, which is supported exactly here. So this is like having delta x, x, which is identically 0, okay? So the system, so it's a kinetic equation that conserves energy, which is just given from the initial dynamics. There are many other systems in wave turbulence where you have a DNS of a PDE, which conserves, let's say, one invariant, and once you derive the equation, the kinetic equation, you get other invariants that appear. That sometimes is quite useful. Okay. So there is one very simple solution of this equation that you can inspect just by looking, which is called the Rayleigh solution. Okay. It's actually very simple. If you realize that you take n of k to be 1 of omega k, okay, you get exactly from this formula omega k minus omega 2 minus omega 1, which is exactly the argument inside the Dirac. Okay, so this implies, and this is a steady state. Okay. I will just introduce a notation that is useful. In the literature, the right-hand side of the equation is what we call the collisional integral, and it's often denoted by STK, okay? And this, we call it the collisional integral. Okay? So if evaluate the collisional integral and Rayleigh solution, this is identically 0, okay? It's not what we are interested in today, because these solutions are what we say thermal. You see vanishes exactly each of these terms independently, okay? So which will be, that means there is no transfer of energies between cases, okay? In that sense, it's a kind of trivial, okay? And we are not interested in that today. If this is a thermal solution, okay? Basically, there are no fluxes. Okay, this will be even clearer in 5 minutes. Okay. Also, you need to be careful because this type of energy has infinite energy. Okay, so the energy. So if M Rayleigh genes will be omega k. Okay, but this is 1 over omega, so this is formally infinite. Okay, So these are ultraviolet catastrophe, which we'll always observe in thermal solution in a classical system. So if you want to make sense to this type of solution, you need to use a UV cutoff. And there's a nice statistical mechanics game that you can play with that, but it's not what we are doing today, okay? And the last thing I want to say about this Rayleigh-Jeans, that there is an H theorem, which is actually super easy to prove. If you define an entropy function which is just the integral of log, it's just a trivial calculation to show that ds by dt is greater than 0, greater or equal than 0. Okay, so entropy will increase, and as usual, if you maximize entropy with a fixed number of with a fixed energy, you will get this solution. Okay, again, you need to put a UV cutoff to make sense to all this. How you prove it? You just take time derivative of the entropy and play exactly the same game here, changing indices, and you will easily prove that it's completely positive. What is more interesting is the flux solutions. Okay.
Entropy, just because it's positive?
Because it's no, it's not necessarily because basically this quantity. Okay, so it's an entropy functional that show you that the system, if everything goes, I mean there are no singularities, this should increase all the time. Okay, you can show that ds by dt is 0 if and only if n is equal to n of Rayleigh-Jeans. Okay, so that's this function has to grow all the time and can be only saturated at Rayleigh-Jeans. It's really what is a way that the system is. I mean, it's something that forces you to go to equilibrium. But you have to keep in mind that this solution have a formally infinite, okay? Because you need a UV cutoff. But if you put a UV cutoff in your system from the beginning and you stayed with that, everything makes complete sense. And there are many things that you can say with the entropy thermal solutions about nonlinear chains that have been used, okay? But we are more interested in turbulence, and for that we need fluxes.
And why do you call it a thermal solution?
Because here, I could have put a temperature. Okay, and basically the constant there is related to the energy. Okay, it's somehow this solution is satisfies the tile balance inside the kinetic equation. Okay, there are no flux, not a change. It's really something on equilibrium. And there have no flux. Okay, that will be even clearer later. So what's more interesting is the flux solution. Okay, so I remind you what we are interested in flux solution. The idea is with to kind of bring the concept of turbulence is that, let's say if this is of k, and of k, I will inject energy here. I will dissipate here. Okay, and if these guys are well separated in space, you expect to have some kind of power law here. Okay? And here the idea is you have a flux that we call P in turbulence, not epsilon. Okay? I just use P. And you have a constant flux of energy along the scales. Okay? And you expect if you have these two guys infinitely separated, okay, this should be a steady state of the kinetic equation, okay, and this is what I'm going to show, okay. So the idea is the following. So if I want to get power laws in my system, everything has to be homogeneous, right? Okay. If the functions, the physics is not homogeneous, there is no chance to get beautiful spectrum, okay. So for that, we are going to consider that omega k. First of all, it's isotropic, okay, and goes to some power alpha, okay. Then I will also say that my V K1, K2, K3, so this matrix that contains all the physics, they are also homogeneous functions, okay. So it means that I multiply all my wave vectors by lambda, okay. This is the same that lambda to the beta be 1, 2, 3. Okay? So these parameters give you basically the physics of the problem. Okay? And we are going to assume isotropy, as what I'm saying here. What does it mean? Okay, it does mean that there are no angular dependence. So if I look for the wave action spectrum, which is a priori a vector, a function of k vector, this will be just a number a, which I don't know, times the modulus of k to some power nu. Okay, and the unknown here okay, and a and nu are the unknown. Okay, so what I want to do now is to play with the kinetic equation to see what should be a and what should be nu, if I can say something. Okay, so for that we just need to count. We can count powers. So if you remember how is dm. Okay, so this is what we say the collisional integral. And roughly this is an integral, so I don't need to write everything. Okay, b1, k12, have 1 delta in k. I just need to count powers, okay, to isolate things. Okay, have some delta in a big omega. I have 2 ends, and I have 2 k's. What I mean by counting powers is that you will use homogeneity of the kinetic equation to get rid all dependence in k. Okay? So typically you will say that k1 will be k times q1. You change variables. This is the new integration. K2 equal to k2. So this integral become an integral in k1, k2. So if I do the same here, this guy here will give me a k to the power 2 lambda. Okay? I just play around, that's give me a 2 lambda. This guy here is a Dirac, so it's k to the minus z. This is a delta in omega. So this will give me a k minus alpha. Here this is my solution, so I will get an a squared k minus 2 nu. And here I have 2 dimensions, k 2d. Sorry, I said beta, it was beta, to beta. This is what I wrote, yes. Okay. So now I have basically, if you do this change of variables inside the integral, you can take all this k outside, okay? And you can find that this guy will be a squared, because we have 2 ends, k to the 2 beta minus d minus alpha minus 2 nu plus 2d, which gives you 2 beta, okay, minus d minus alpha minus 2 times some function, okay, of nu, which this is a priori some very specific, very explicit function. Might exist, might not exist, but it's at least a formula. Okay, so now you see, and this is the right-hand side of the equation. If you admit that you want pure power law solution, okay, the right-hand side of this equation, it is exactly that, okay? So nu is a solution. Basically that's it. If so, if this is what we call the dimensionless collision integral vanishes for some given exponent, then t of k is 0, okay? And then you have a steady solution. So the first example This is easy to show. If you take I of alpha, this is 0, okay? This is what I showed before, just by definition. But this, as I said, these solutions are a bit boring, so we want to get fluxes, okay? So the energy spectrum on the fluxes okay, so you have the energy. So this is what we call the one-dimensional energy spectrum. So it's the energy that we integrate in a full shell, okay? So the energy is omega k, and okay, this is the energy contained for a one given by vector, and you have to integrate over the sphere, okay? And here you have the element of area. So omega in dimension 1 is just 2, omega in dimension 2 is 2 pi, omega 3 is 4 pi, and so on, okay? And if you want to have flux, you would like to write the kinetic equations as a conservative equation. So you want to see, you want to write dt ek is plus dpk at k equal to 0, okay? So this is a trivial game, okay? You just, this guy is, you know it from there, okay, from this tk. If you write here, okay, it's easy to see that dkp this is basically minus the right-hand side of the equation, okay, multiplied by this guy here. Omega d k d minus 1 omega k is tk, okay? And we are almost done. Maybe I can switch off the light, right? No. Can you see who is in the shade? That, okay. Okay, and now this, as st of k was just there is explicit solution in k, you can just integrate between 0 and k. Of this guy that is there. This is omega alpha, if you make the sum, okay? It was 2, so I changed this was little d, okay, of k, kd minus 1, k alpha, stk, dk, and that gives you something very explicit, which is minus a squared omega d k a la 2 beta times I of nu divided by the same exponent. Okay? So this is a direct calculation. So the flux at the scale k is given by this power times this function. Okay? So now I'm just looking for let's say a candidate for the solution. Okay? If I want my flux P of k to be constant, okay? What I could take is just need to take this power to be 0. Okay? Okay? So this will be my solution. But as you see here, I have the same power. Okay? So I need also this is a condition. Okay? Furthermore, I need to be well defined. Okay? Okay? So let's assume that you have these properties, okay? That I of nu star, okay, which is given by this quantity here, okay? So nu star is just beta plus d, okay? So this is the candidate you're looking for a constant flux solution. So if nu star is this, and you also have that I of nu star is 0, and its derivative is fine, well, then you're happy, because you get, okay, you can relate the flux P0, okay, to the constant. There is no K dependence and a simple L'Hopital rule. And you have a -2. Okay? And now you have A as a function of the flux. You have nu star, and you can bring it back to your original solution. Okay? And that gives you what is called the Kolmogorov okay, which you can just write Kz. Okay, so this looks pretty nice, and this is a solution. You see, this is something you can compute analytically a priori, okay? And then if I input in my system a flux of energy P naught, then this should be the solution, okay? That carries a constant flux. So this is very nice, but of course I'm doing a lot of assumptions, okay? And we need this solution to be valid, okay? And there is a definition, okay? Okay, we say that, how we call it, which is the concept of locality. Basically that the solution is valid. Okay, so I will just rewrite what I mean by locality. The first thing you want is that nu star. So the locality is that the solution n of k, a k to the minus nu is local. First of all, you need that I of nu star to be 0, okay? And you know that you need to differentiate it around this solution, okay? In order to do this L'Hopital rule, okay? Should exist. Okay, basically you want that E of nu to be C1 around nu star. Okay, so it's kind of a smooth. And this is the kind of the first notion of stability, the poorest notion of stability you can imagine in the system, okay? So if you have your solution that is not, I mean, if you move a bit exponent and this guy diverges immediately, okay? You expect that this solution could not be realizable in physics, okay? And you need to be, all the collisional integrals should be kind of smooth around this solution you're postulating, okay? If such is the case, at least you could expect to have some chances the solution to be stable. If you want to really prove the stability, this is another matter, okay? So now I would like to explain something else, okay? Which is, what are actually these solutions, okay? Okay, but let's rewrite the solution. Sure, please ask questions. You have been very silent. Maybe the party just was too wild.
So the beta comes from the definition of your problem, right?
The beta, yeah, beta is physics. Everything here is beta is a nonlinearity, related nonlinearity.
And from your construction, you show that the only candidate for a solution is this b plus d, so it's completely a beta plus d.
Exactly.
Why on earth should that
this is a good thing, okay? So it's the other way around. If I want to have a flux that is constant along a scale, okay, this is the condition that the exponent should fulfill, okay? It's something you have to check a priori. And there are ways of doing it, which I will show in a second, which is called the typical way that you can find this exponent with a bit more of calculation. But remember what are you doing, okay? So you have plug a power law solution in an integral that goes from 0 to infinity, okay? Many integrals that go from 0 to infinity. So power law will never a priori converge in 0 and infinity simultaneously. So what's going on that there are different terms inside the kinetic equation with plus and minus that have to cancel exactly in a good way, okay? Such that if I plug a power law inside, everything cancels nicely and things get convergent. It's kind of a strong constraint, right? But I couldn't say most of the spectra in wave turbulence theory fulfill that, but there are many of them that they do work. And then it's an exercise, a calculus exercise. You plug this power law and you have to study the convergence property of this function. So you look at the bounds in ultraviolet, infrared, and you get bounds for the existence of this function. Okay, it's case by case study.
Isn't mu equal to beta minus d?
Say again?
Isn't mu equal to beta minus d?
Here? There should be a mistake, right? Or maybe I did a stupid mistake or not. It's 2 beta minus 2d minus 2 nu. This should be beta minus d. Yeah, I probably did a mistake in some of the calculation because I know this will not work, but well, probably somewhere I have a nu that was minus nu, okay? It's a stupid algebra. So this is typically the exponent, okay? Let me check this, just a stupid mistake. So I of k, where is the flux? I of k was minus 2 nu, 2 beta, minus. Yeah, I think there are plenty of typos, huh? So it's 2 beta minus d minus alpha minus 2 nu, 2 beta, and then dpk, well, 2 beta minus 2 nu, somehow it should be 2 nu. I'm a bit surprised. Beta, so it's plus 2d, right? Yes. Yes, it should be plus, okay? Because this, I know that it's, this is the good results, anyway. Okay? So now, the idea, I will just rewrite a bit this equation to try to formulate what is KZ solution, okay? So let's rewrite the equation. Okay, so I will take just the omega d, kd minus 1 omega k stk. So the stk multiplied by the energy density, which is omega d a square omega d a square k2 beta plus 2d minus 2 nu minus 1. So it's still just plugging a power law, okay? Playing this guy, I know it from there, okay? And I can rewrite, if I had I could take the expression for the flux, okay? Wait. If I replace everything, so I will get 2t. let's take, I will just take my A, okay, from here and replace it in this solution, okay? And that will just give me 2p k to the minus nu star minus 1 I of nu, okay? I'm just kind of rewriting things. I haven't done anything. So this, if I assume that my nu star is indeed a solution, so I can Taylor expand, okay? So this guy here is roughly I of nu star, which is 0. So it's di I d nu star, nu minus nu star. Okay? And then this is, there is a minus, so this I can write it, if I do one more step, so I had nu minus nu star, which is small because I will be taking nu going to nu star, okay? And then I get this, okay? I will get P0, K, eta minus 1, eta, this is, sorry, should be 0 over okay, this is a mistake. Eta exactly that, okay? Omega k okay, so this is an eta is a small thing which is just 2 nu, okay? So basically there is an exercise you can do. If you have k this go in the sense of distribution to 2 delta of k when eta goes to 0, okay? This is an exercise from math you can do. It's a very strange approximant of the delta, okay? But you can prove it with a test function. You multiply it and do the simple math and you can show this perfectly, okay? So why I'm doing that, okay? I prime that goes out, okay? It disappears. Just a second. So sorry, here, this is I of nu over I prime once I replace the value of A, okay? And then when I Taylor expand I, the derivative cancels out, okay? So I get this equation. So what is then a K-set solution? What is the... So a K-set solution satisfies so that is a K-set solution. In this sense, this is a non-conservative solution, okay? So there is a dissipative or non-conservative, if you want. Okay? It can be in general non-conservative. Okay? I'm kind of rewriting anything, but if I just write dE by dt, the total energy of the system, which the integral of this guy between 0 and infinity. I integrate this from 0 to infinity. The 2 gets out, and it's basically minus P0. Okay? So the cascade solution dissipates somehow. Okay? And this is the only way to sustain a flux solution in the system. Okay? So if, in that sense, this type of solutions are not strong solutions of the kinetic equation, are weak, because you need to understand it in this way. Are 0 everywhere, but at 0. Okay? For a particular case of the energy cascade, actually you want to solve this equation with P0 that is positive. Okay? Which is what you really expect. Okay? If you are not able to find a solution of this equation with P0 positive, it will be something that's a bit pathological. Okay? So this type of non-conservative solution, it's valid for actually for all type of cascade in the system, okay, not only for the 3 waves. So in general, okay, if you have an invariant capital phi that we can write like such that d phi by dt is equal to 0, okay? A cascade solution associated with that will be basically the same thing, kd, but here you will get invariant ρ k minus 2 some q naught delta k, okay? And then you want to find solutions. You will find the solution in the same way I show, okay? But if you want to see it in this sense, then if Q naught is positive, that will be a direct cascade. And if Q naught is negative, an inverse. Okay? And if you do it for system with double cascade, this is actually what you find. Remember that this Q naught is not arbitrary. It's related, once you found exponent, to the derivative of the collisional integral. So depending if the things are good, this guy will have the same signs, the good signs. Okay? So this is for the isotropic systems, which are kind of simple. Okay? And the last thing that I need to discuss on the blackboard is what happens when the system is anisotropic. Okay? For that, I forgot, yes, just a last comment, okay, which is, could be an exercise, too, is the Sakharov transformation. What I have is tk, is the integral, you have 1 rk, 1, 2, R1, 2k, R2, k1, okay, times the other things. So it's an extremely clever change of variables, okay? You would like to change variables. Okay, so in R1, K2, you take K1 to be K squared over K1 to L, and K2 equal to K1. Okay, so you change variables in this way, in this one, and then the second one you do the same, but you change 1 and 2. Okay, you do this change, you close your eyes. These things might not converge, but you do it anyway, and this way. And if you do that change of variable, you can show that st of k becomes something k1, 2, which has all the other things, but something else now, which comes from the for the determinant of the change of variable, k1 to the y, where y is exact alpha minus 2 beta minus 2d minus 2 nu. Okay? This is just a change of variables. It's a direct algebra. You don't care about convergence. You go to the end and get to this change of variable. Okay? And then if you remember that inside this guy, there was a delta of omega. I have a k to the y here too. This omega k 1, 2. If I say that this exponent, if I say that y is equal to alpha, then what I have in the kinetic equation is something like delta omega k 1, 2, omega k 1, 2. Okay? So this is the way that Sakharov showed his solutions. So if y is equal to alpha, again, you get the Kolmogorov nu k star is beta plus d. Okay? And on the hand, if all the manipulations you did in order to change variable here are correct, it means when you're doing change of variables, everything converges, then you're proving that this t of k is exactly that, and then kz solution is 0. It's a real set of the I. But for that, you're doing nasty things. So you're bringing infinity to 0, 0 to infinity, adding them, hoping that it's finite. Okay, and this is something that we have to prove case by case. Okay, so now we are gonna, I don't know if I'm even going slow. So we now go to the isotropic system, okay? It should be a bit simpler to explain now.
So are they observed on the PD, these power laws?
Yes, yeah. I mean, I can show many examples where, for the case I will discuss today, not really, okay? But if you take NLS, inverse cascade, super clean. I think for capillary waves, it's also quite nice, okay? And you have a bunch of systems where you do DNS, it's fine. Experiment is always a bit more difficult, obviously.
And does it exist in the literature or the same study, but when you, in an artificial manner, when you include forcing and dissipation, do you reach statistically?
Numerically. Numerically, yes, that's what to do. But mathematically, no. So the KZ solutions, if you want to state it, are that. They are non-conservative solution of the kinetic equation.
Yes.
With the Dirac in 0. This is the statement, okay? Studies numerically, yeah, there are many, okay? Well, not too many of the kinetic equation, but for DNS, trying to get this, yes. And in many studies, you can actually compare the value of the constant, and it works. When the theory is fine, and everything is kind of well controlled in the theory, then you do the numerics, and it works. Then it's like proving a theorem with numerics. So if you do the numerics correctly, it has to work. Can be difficult, huh? Oh. Okay, now let's consider anisotropic media, okay? Okay? So the first thing, so yeah, we want to look for flux solutions. Huh? So you will do the same. You will write dt E of k. This now guy is a vector plus the divergence in k of some flux that now is a vector. Okay? And that's what Giovanni was discussing yesterday. Here, the question is, what is the flux? Okay? Which is actually not so obvious because there is a gauge freedom, right? And what is A? It's not very clear how to choose it. Huh? In the end, what it matters is how you transfer energy. Okay? So this rotational will go away, but you would like to have a notion of vector field that kind of tell you how the energy or the invariant is being carried in space. But we are not going to discuss much the things about the flux. We will just look about the solutions. Okay, you can. As we don't have an obvious expression of the flux, you cannot repeat the same kind of very easy argument to get the cascade solution, but you can do the equivalent of the Sakharov transform. Okay? Okay, so for instance, we are going to consider in 2 dimensions a spectrum which will be a constant times kx minus nu x. Okay, for instance, also omega will be kx alpha x, ky alpha y, and so on. Okay, so the same arguments that it's by a homogeneity of what discussed before, you do it by components now. So here are, of course, absolute values. Okay, you could imagine also 3D case where n of k, now you say that it's a function of kh to some power minus nu h, okay, times kz. This is what we're going to do in inertial waves, okay, with some omega, okay. Here also you will have a dimension, okay, dx, for instance, in this case will be 1, dy will be 1. If you consider this case of isotropy in cylindrical coordinates, so then dh is equal to 2 and dz equal to 1, okay? And now you formally can actually just look for do what is called the Kuznetsov Sakharov transform, which is the generalization of the which is formally identically to the Sakharov transform, but you treat component by component, and you can find that nu now look as a vector. So this is nu x, for instance, nu y. It's just as before, it's actually the same thing. Beta plus. Okay, so you use the homogeneity of the equations component by component, okay? And everything goes the same as before. Okay, and now you want to do the same. You want to understand what are the. You would like to write actually where it is. You would like to see what is if you take a cascade solution, okay, which is this. So this is associated with a flux. You would like to do the same as before. You would like to plug it in the collisional integral and see which kind of singular solution is. Okay. So for instance, you take omega k stk, okay? You do exactly the same exercise as before, okay? And you will get, well, an a squared kx 2 nu x minus nu x star minus 1 I of, okay? This is just exactly the same as before. And now you say, okay, I will say that this guy is a good solution of my I function, my collisional integral. So this is I of nu x star nu y star, which is 0, okay? Plus the linear correction. So it's di nu x nu minus nu x. You do it component by component. Okay, and then this is an issue, okay, because this is 0, okay, so we'll do it. Nu x Okay, for instance, you have this term, okay, which is di at the nu x. Okay, so you see here when I take, sorry, nu x star. So you see when I will take nu x going to nu x star, the solution, okay, this term with this term will give me a Dirac as before, okay. However, this one, I will take nu y going to nu y star and just give me kx minus y, okay. So if I take the first limit here, I'll just get x squared, this and this give me a Dirac on kx over k, and this guy gives me ky minus 1 times dy. So now it's something that is way more strange. So this is the solutions of, this is what a biohomogeneous solution satisfy in an isotropic media, okay? So this basically I can rewrite it again. So will be some fx okay? So it's a very strange type of solution, right? Okay, but this is what it is. Any bihomogeneous solution of the kinetic equation is first necessarily solution of this, okay? So this is the question, and this you can imagine that this is the type of forcing you're putting in the system. So it's the first question, is this something you could find actually in any experiment, which is certainly not obvious. But anyway, we can interpret a bit what is that, okay? Okay. So now, this is kx, ky. But let's say, for instance, that fx is positive and fy is negative. Okay, it can be arbitrary signs. Okay, so this means this is a kind of a forcing which is supported at k equals to 0. Okay, so it's very strong. So it's very strong here, but it's infinite here. Okay. And there is also one supported on ky equal to 0. Okay? If fx is positive, okay, it seems that it acts as a source on ky, which amplitude is a bit like this. So for instance, this will be like everything is flowing in this direction. Okay? If fy is negative, okay, this will behave as a sink. So now if you imagine you're forcing your system here, okay, would you expect that the flux should do something like that, okay? And that will be the flux, what you expect from these solutions, okay? So this is the behavior of this bihomogeneous. But there is one thing, that fx over fy is not arbitrary. It's dy at the nu x by the nu at the nu y. So this bihomogeneous solution of the kinetic equations are very peculiar. You really need to say that the forcing in one direction is fixed by some proportionality constant to the other. So this, for me, something that's puzzled me if it's something that we can really find even in a numerical simulation. The last thing I want to say, so imagine that you look for the solution of I, okay, and the plane nu x, nu y, okay? So here, let's say that this is the cascade solution. Okay? And let's say that it's a good local solution. Okay? What does it mean that it's local? Which is everything is finite around this point. Okay? It's not degenerate, so typically we could imagine that here the function I is C1, okay? In this vicinity, in the neighborhood of this point. If you say, also generically you will have that the gradient of the function is different from 0. Okay? It could be that it's 0, but there is no reason that it will be always 0, okay? If this guy is, the I is non-zero in this point, it means that you can invert. So you are solving an equation, I of nu x, nu y equal to 0. And you know that this function goes from 0. If the gradient is non-zero, you know that typically you will find a family of solutions. And all these family of solutions are valuable, are good candidates because they are inside the window of locality. Okay? So what this tells you that in the kinetic equation, when you look at anisotropic media, you have an infinite number of solutions, and if one is good, you have immediately an infinite number of good solutions that are good candidates. And how to pick them? The only possibility is that when you force, you should have some specific ratio. And if you don't have it, perhaps the conclusion is that you will not have a homogeneous solution. So mathematically, this is a huge constraint. If you run an experiment, you will just force at one frequency and one wave vector, and there is no way of controlling one or the other. So that maybe that's the reason why it's so difficult to observe the cascade solutions in experiments and numerics. Okay, so now I can move to my presentation and talk about a bit inertial wave. I have like 20 minutes, right? So if you want the conclusion up to this point is that when the system is isotropic, everything works really nicely. We understand it quite well. Solutions are fantastic. We can check it numerically. Anyway, as soon as the system is anisotropic, everything gets way more complicated. And even the pure power law solutions, one by my question if they have any relevance. So I will go quite quick here, okay, because I have much less time of what I expected. So I have expected to make two small detours about a bit different subject before going to kind of internal inertial waves. So this I will really skip it, so you can close your eyes while I'm passing the next 5 slides. Okay, so it was some comments about how the cost of numerical is solving either DNS or wave kinetic equation. I will just make a very short comment about this. Okay, so if you want to solve the kinetic equation numerically, okay, what you have to solve is this equation. So this is can you turn it on this? Okay, so you have to solve a differential integral equation. Okay, so the first thing you need to know what is this resonant manifold. So if you know it analytically, it will help. Let's just say you know it analytically, and then you have for an n-wave system, you have n-1 integral, okay, to perform in d dimensions. Thanks to this delta, you take one less and one integral less because of delta n omega. And suppose you put m grid points per direction, you have to do it for each grid point of your spectrum. So if you multiply all this, it typically costs m to the n-1 d times d minus 1. Okay, just an example. If you look at, for instance, at the 1D MMT model, which is Giovanni torque roughly, if you put m points in your spectrum to discretize, this will cost you m squared, which is totally fine to do in numeric. Let's say you do 3D NLS really stupidly, you took kx, ky, kz, 3-dimensional, has a cost of m to the 8, which is impossible to do in any computer simulation. If you are a bit clever and you say, okay, I would say that it's isotropic, then you reduce it to m cubed, okay? And if you look for internal or inertial waves, which are a function of kh and kz, the cost is m to the 4, okay? So even if you solve the kinetic equation, which is kind of supposed to be something useful numerically, for this type of system can be quite costly anyway. Okay, so that's what's the comment. So this I will skip, okay, and we'll go a bit to the inertial gravity waves, which was actually the title of my talk, okay? And why are important in the ocean? Okay, because this is this is a typical picture you will see in in most of the talks about internal waves, that because of the topography of the ocean and the tides, okay, you excite inertial waves, okay, and the main question one of the important questions in the oceanographic world is the mixing in the ocean, okay. So the main question, so energy is injected, let's say, at large scale because of the tides and the topography, and it's dissipated at small scale by viscosity, wave breaking, and like a real hydrodynamic turbulence. And the point is how you connect these two, okay? And this is understood that the nonlinear wave interaction is actually the process bringing the energy toward the smallest scale of the system, okay? And typically, people in the oceanography community see turbulence, a hydrodynamic turbulence, as a sink of the downscale internal wave cascade, okay? So for them to parameterize models in the ocean, they need to understand how much energy the internal waves transfer. So if we go back to what I quickly showed yesterday and what Julien showed the evening, okay? If you look at the inertial gravity waves, you put a Coriolis, you put this rotating system with stratification. The dispersion relation is this one. Often in the oceanography community, they take the limit, the hydrostatic limit, where kh is much smaller than kz, okay? So the cosinus is 1 and the sinus is just kh over kz, okay? And I get typically this dispersion relation, okay? So you immediately realize that the frequency is bounded by f and n. In the physics community, we always look at the spectrum in wave vector space, kh, kz, but the sonographer typically look at an omega kz, which is natural to the measurements. So what they do, they put a device in the ocean and many in the deep water, and they just measure things there, okay? So they know the position in deepness, but measure only time, okay? Whereas measuring kh, it means like kind of dragging a device, but then it will be more difficult to have kh, kz at the same time. So I don't know if probably they are able to do it now, but most of spectrum and data that is available is of this kind. Just you look at how important could be rotation or stratification in the ocean, okay? If you plot n over f, and so Giovanni just sent me this picture a couple of days ago, and you plot it versus latitude, okay? You see that there is obviously a huge dispersion, but typically over here, n over f is around 50, okay? So meaning that you can, in many situations, neglect the rotation, okay, and just focus on the internal waves. I should mention that there is one very famous empirical spectrum, which is due to Garrett and Mank, which is on the in the 60s, which is an empirical formula based on dimensional analysis and a very nice understanding of the physics, but it's a huge formula with many fitting parameters, okay? But here I changed a bit the notation as I was doing copy-paste from other papers, but m now corresponds to the vertical wave number, and k here is horizontal, okay? So this is the spectrum in k and m, okay, which will be interested from the kinetic equation. You can pass, you can use the dispersion relation to express only function of omega. So you do all the good change of variables, integrate along the other direction, and you get this formula, okay? And basically, if you consider that omega frequency that's much larger than the Coriolis parameter, okay, and m much larger than this reference wavelength, okay, you can get what is called the Garrett-Mank prediction, okay? And if you integrate over dimensions and properly, you get an omega that goes like omega minus 2 or kz to the minus 2. This is just empiric formula, so there is no theory behind. What it was nice that in the 60s, when they came out with this formula, they used data of so-called the site D. Okay, these are observations, and they fit it nicely over many decades, and that was a kind of fantastic prediction. Of course, then the people perform many observations. What I'm plotting here is the exponent of the spectrum measured in different parts of the ocean, different campaigns, okay? So now it's the exponent for n, okay? So you can pass from n on energy. But basically here is the exponent of kh and the exponent on kz, okay? The Garrett-Mank is this one there that fits nicely where it was produced. But if you look at the data in the ocean, it's kind of really scattered everywhere in this plane. The kz solution is this one there, which I will explain a bit later. And another available solution is this one. So there is no clear understanding what are the exponents in the ocean. And if you, it's kind of natural if you're looking at nonlinear waves, okay, to say, well, we should do wave turbulence theory. And this is something super old. Actually, I guess you know this guy, okay? It's kind of, it's Nobel Prize. So he came out with the kinetic equation, the first statistical description of waves in the 60s, okay? And since then, there is plenty of people who have worked improving and improving either the derivation, generalizing the things, okay? And I'm adding here more recent papers which are really focusing on the derivation of the kinetic equation. So if you see, for instance, they do a Lagrangian approach, Eulerian, taking the fields. Some of the derivations has rotations. Some of the derivations include the rotation, some other they don't, okay? Some of the derivations are doing canonical variables, so they're beautiful, other they are not, so they're terribly easy and difficult to follow, okay? And I will just quickly comment these two, okay? In particular this one, okay? As I really want to go to the results, which is perhaps the most elegant one, okay? But before going to stratify, I'd like to make a comment on the inertial waves, okay? Which is, we know the spectrum thanks to a paper by Sébastien Galtier. He simply took Navier-Stokes under rotation, do the wave turbulence theory, use what is called the helical decomposition in order to get this equation, and then perform all the theory to get the kinetic equation and find the KZ solution, okay? Which has this exponent. So that was done in 2003, and 20 years later, he managed to check that the solutions were actually solutions. So what I'm plotting here is what I call the windows of locality, okay? So he looked at the collision integral as a function of the exponent, okay? And he found that over the blue region, okay, the integral is convergent. Nicely, the KZ solution is this spot in the middle, okay, showing that the solution that he found in 2003 is actually a good solution, at least from the kinetic equation from the formal point of view, okay? Furthermore, they compute the fluxes, okay, in this spirit and show that the flux along the vertical direction is much smaller than the one in the perpendicular. Okay, so everything goes basically in the perpendicular plane.
You pointed out carefully that in this 2D case you'll never have just a single point, but you have to have a single point.
Exactly. So this we don't know actually. It should be a curve. I have no idea where it goes. Okay, but this is the KZ solution, which at least is the best candidate. But indeed, you could have many solutions. And the problem, obviously, if you think about rotation, the first thing that comes to your mind, yes? Yes?
The rotating faces are andstratified.
Yes.
And you gave the equation for the exponents, I equals 0, which is a function of the two exponents.
Yes.
And so it usually doesn't have a unique solution.
It doesn't.
It just has a family of solutions.
Of course.
As you said. Now, you just quoted one of them, Galtier. Now, why that one?
Should be the most important one. Is the one that is associated with an energy flux. Okay, but it's the only argument that tells you we should look at that one. But I completely agree. There is an infinite family of solutions, which a priori they are all good candidates. But if you should start by looking at one solution, I think it's the one that carries a constant flux of energy.
But why that one? Why that one?
Why I should take the one with constant energy flux? For me, I agree that for me it's the most natural one, but I believe that it's more natural one because I just...
But the condition on the energy flux gives you a continuum.
Absolutely, yes, there are infinitely many solutions.
-5 and
Yes, but this is very particular because this is really associated with a constant energy of flux of energy along a scale, which is at least what you expect to have. The other solutions, they are also solutions, but they are not associated with a constant flux of energy. What they are, it's something that is really worth studying, probably with experimental numeric of DNS, it's too difficult. Kinetic equation simulation is the way, probably.
Solutions of the kinetic equation.
We don't know how to find them.
We could find it numerically, for instance. Okay. So these are the beauty that you have also analytical expressions, right? But let me go a bit farther because I'm really running out of time. 5 minutes will be almost impossible, but okay. So if you think about rotation, this is the image that comes to your mind immediately, okay? These huge Taylor columns, which is a completely coherent structure, which is against the random phase approximation assumption, okay? So you say this cannot work. But then if you're doing numerics, as in the group of Benjamin Favier, they say, okay, I'm doing numerics, I can remove these modes, okay? If I remove this mode, then I get something that looks more wavy, okay? And they look something, well, they got at least a bit closer what the exponent is, okay? From the experimental side, okay, in the group at FAS, the group of Pierre-Philippe, they obviously try to do the same thing, okay? But if you rotate, you will observe the same Taylor columns, so they wanted to dissipate them, and then they added a honeycomb in the bottom and the top. So this column could not really create it and will be dissipated by the experiment itself. By doing so, they obtained a spectrum which looked kind of nice. And if you took the high Reynolds ones, okay, and you collapse it by omega epsilon, so the scaling with the flux, kind of collapsed with a power law which was, let's say, over almost one decade, compatible with the scaling. We still need to check if it's a good solution by computing the KZ constant, okay? And this has not been done. It could be possible from the last paper of Sebastian. If okay, I will probably just be quickly about the wave turbulence theory, okay? If for the stratified fluids, perhaps the simplest and more beautiful paper is the one by Herbault and Tabac in 2001, where instead of taking Boussinesq's equation, okay, they use the hydrostatic approximation, okay, then use isopignal coordinates, which is density and deepness are one-to-one related, so I can express fluid dynamics in terms of rho. And doing so, they found that the equation of motion has a nicely Hamiltonian structure. And once you have Hamiltonian, it's just the standard machinery to get a Hamiltonian with the interaction coefficients, from where you can get the kinetic equation, okay? So I will skip this other derivation because it's too long, okay? And I will talk about the KZ solution for internal waves, okay? Which actually in the oceanographic communities is known as the Pelinovsky-Raevsky solution, okay? Which is from the 77, okay? This is the exponent. In 2010, Lvov et al. Studied the validity of this solution, okay? So this is again the same plot. They're looking for the window for convergence in A and B of the different exponents, okay? And the integral converges in the gray area and the ultraviolet, okay? And the infrared, it converges in the blue and in the gray area. Both ultraviolet and infrared, the KZ solution is outside, okay? So this doesn't mean that this solution is not a solution. You should really discard it. And if you have a hope of having solutions, it should be in the intersection of these two. Okay, so the KZ is no solution, and there is only one intersection, which is in this line. Okay, well, they say let's stand on this line, okay, which is B equal to 0 and A between these bounds, and they look numerically if the collisional integral vanishes for some value of A, and it does, okay, which is at this specific value 3 point something. And this is one of probably the only solution which is at least mathematically valid in some sense of the internal wave kinetic equation. But it has a lot of issues, okay? And in some sense, it's the only bihomogeneous solution that is possible to have for the internal waves, the only one, okay? It's close to the Garrett-Monk spectrum, which is the spectrum that people should look. However, the collisional integral is not differentiable, so you cannot change slightly this parameter, okay? So it means that approach raises a lot of issues about realizability of the spectrum. It's something you could observe, okay? If you go to the experiments, okay, it has been a big trouble to obtain them, okay? So this experiment again in the group of Pierre-Philippe, but this time is no rotation, but a stratification, and they try to go there, and basically they observe a lot of kind of discrete turbulence and interaction with the bound standing modes of the system, okay? Then they try to do something similar to dissipate this bounding mode to changing the geometry, and they got a bit better, okay? And they could kind of get rid of this discreteness and start looking to turbulence. But basically, if you look at the omega k plot, which is a representation of the waves, it was just very few waves, and basically it's very far from what wave turbulence could be. Okay. Then from the in fast, okay, Nicolas Mordan was also doing the same. The spectrum were not super beautiful neither, okay. The problem is that if they forced to match, they mix all the salt in the water and then there's no stratification, so they cannot do much. But they did it anyway, and they have these beautiful movies, which you see the wave breaking, okay. But we are not talking about wave turbulence here. It's something, if you look at the omega k plots, it doesn't really look like a curve where you can say that you have wave, okay. So that was very difficult. So I'm really rushing, so I just want to show doing DNS doesn't really help. We tried to do the same, remove vertical modes. We didn't get anything good, okay? So then we turn out to look at the kinetic equation. So we look at the kinetic equation with forcing and dissipation. So that was by Vincent Labarre, okay? And basically, you don't know what to do. You run in the middle of the box and see what happens, and that's what happens, okay? This is typically one kinetic time, which is 1 month for the ocean or like 3 hours for the experiment, okay? So it's everything but what you expect from a cascade. The cascade will be something like some kind of diffuses like a front, and this goes in very specific directions. Well, so I should really go a bit faster. Huh? These specific directions are instabilities that are well known since the 70s, okay? They are related to non-local interactions, okay? Which depends very specific. Two vectors are symmetric, the two have similar frequencies, and then you can study them. Particular, I want just to show one of this type of non-local interaction that was studied by Philippe. If I can have 3 minutes, 5 minutes for the time lost.
Yes, I mean, it's too bad though. It's very interesting. But
yes,
it's very over.
Yes. Well, I will show. There is one extra theoretical prediction, okay, which you get from this equation that was done by Per Philippe, where you, from the kinetic equation, you do some reduction, get a diffusion equation, you can solve it, okay, and get this exponent. And we just go to show the last one, okay. So then you can do simulations of different cases, okay, and I will focus on one simulation with you folks. You put some forcing in this size of the box, okay, and you let the system to evolve, okay. It takes long time, to about 200 linear times, which is, it will be like 600 hours for an experiment to get something, okay? But once you get this steady state, okay, then you can start measuring the spectrum along dimensions, okay? And what you obtain is what I wanted to show to please one of the organizers, okay? And if you look at cuts of this spectrum, okay, we were forcing at high kh, low kz, you start observing beautiful power laws, which exponent nicely fits the prediction of Lanchon-Corté, okay? So if you want the summary, at least for the anisotropic system, if you start looking in one direction, you might see Lanchon-Corté prediction. You look in another direction, you could see Lvov. You look in another direction, will be yet another thing, okay? It's an extremely complex system, okay, which we don't understand much. So we are trying to characterize all the details. And perhaps the two conclusions of these two lectures, the first one is that the wave turbulence theory is great. It has a wonderful power to predict things, but still anisotropic systems, they are very complicated, and we need to really work a bit harder to get to comprehend. Well, thank you. Sorry for going late.